Hey everyone, this is Dr. Calkins. We're going to look at week 2, chapter 3 lecture, all about atoms. So as we look at atoms, we need to know that there are 3 parts. We have this entire spherical atom, and in the middle is what we call the nucleus. That nucleus is going to have our protons, which we're going to use as P positive. It has our neutral neutrons. Those are the ones that cushion those protons, so they don't have to really touch each other as much as they would repel. This helps out. And then in this empty area is what we call our electron cloud, and that's where our electrons are going to go. Be negative. So what's most important about these 3 subatomic particles is protons are positive, neutrons, given their name, is neutral, electrons are negative. And more importantly, it takes over 1,800 electrons to make up the mass of hydrogen, so they have a negligible mass for us. We can almost assume they don't exist in the sense of mass. Their mass is so small that as we round up, it goes away. But the protons and the neutrons, these are what we call the mass of the atom, so this would be the mass number when you add those together. So mass number is protons plus neutrons. What's unique about an atom is protons and electrons are going to be equal. And that's the case for elements on the periodic table. So protons and electrons are equal. That just means you have just as much positive in the nucleus as you do negative electrons around the outside. It's definitely a little bit more complicated than that. We'll get into that in our next chapter, week 3, chapter 4. But these are the parts of the atom that you need to worry about. Protons positive, electrons negative. But protons and neutrons have all the mass together. That's the mass number. So as we look at the periodic table, what we're going to see very quickly is a lot of portrait kind of boxes. You're going to have a number up top. That's called the atomic number. And more importantly, that is the protons. It could be the electrons if it's an element, but we don't want you to think it's electrons always, because you can lose electrons and become an ion. It's a topic for another video. You're going to have some symbol. Maybe there's a lowercase letter, maybe not. There's no longer ones that have 3. And symbols are going to be what we call the atomic symbol. And we have 118 choices. So a lot of them are going to have lowercase letters because we're going to run out of the alphabet pretty quickly. And you're also going to have a number down here. This is called the atomic weight, atomic mass, same thing, basically. The atomic weight is a weighted average of all isotopes. So it is a calculated answer. So there is no easy way to get that number without a calculator, multiplying by the percentage of the isotope and its mass. So that number is difficult to get. What we most certainly don't want students to think is this is a calculated answer here. Mass number is just an addition of protons and neutrons. This weighted average is all mass numbers multiplied by their percentages and then added up. So this is much more complicated than an actual mass number. So let's show you a couple examples of how this works, and we'll do that with carbon. So carbon has a carbon 12, has a carbon 13, and then there's a carbon 14. So 3 isotopes of carbon. There's many more isotopes. These are just the ones that are most common. And again, carbon 14 radioactive, not very common at all, but it's a good example. So I like to make a chart: protons, neutrons, and electrons. Make a chart: protons, neutrons, and electrons. Make a chart: protons, neutrons, and electrons. And see how they're different. If you have a periodic table handy, even if you don't, I'll cut to the chase, and carbon is number 6, so atomic number 6. So if you remember, that is protons. So what's unique about carbon atoms in this situation is if we have a carbon atom, here we have 3, here we have our nucleus. It's kind of like a marble in Busch Stadium. So to give you that 1 in 20,000th kind of scale, if you had to put a marble behind second base in Busch Stadium, the entire stadium is the size of the nucleus versus the actual electron cloud. This distance here is about 1/1,000,000th the size of a piece of hair, but inside of that 1/1,000,000th the size of a piece of hair is Busch Stadium. 1/20,000th of that is actually the nucleus, and in this case the nucleus has 6 protons. If we change that number, it will no longer be carbon. If we're carbon 12, that means the mass has to be 12. That's that mass number. So in order to have a mass number of 12, we need 6 and 6. So this will also have 6 neutrons in that nucleus together. But if you're carbon 13, you got a little bit heavier because now to get 13 as a mass number, you're going to have 7 neutrons. So a little extra cushion inside the nucleus. If you're carbon 14, we need to have a mass of 14. That's these two added together. So remember, that's just adding these together. And that'll be 6 plus 8 to give us 14. We have even extra cushion here. Turns out we have so much cushion that this makes carbon 14 radioactive. Carbon 14 being the isotope used to age things like woolly mammoths. If you're a woolly mammoth eating food, that's great. You're getting lots of carbon 12, carbon 13, carbon 14, but when you die, you stop getting carbon. And what's unique about radioactive atoms we talk about later is they disappear. So if you have a tissue sample from a woolly mammoth, you can see that the carbon 12 never changed. But you can calculate how much radiation is coming off that carbon 14 and know how much is missing, and then you can backtrack that half-life and see how long it's been stuck there, frozen in time. So as we look at examples like this, just remember that protons and neutrons make mass numbers, not atomic weight. It would take the average of 12, 13, and 14, because this is about 99% of carbon, about 1% of carbon, and about 1,000,000% of carbon. This would give us 12.01 as an average. This would be the atomic weight. So again, that's a calculated number, very different than those mass numbers. Last thing we need is the electrons, but remember, for neutral elements, positives and negatives need to be the same. So if you have 6 positive, you're going to have 6 negative. 6 positive, 6 negative, 6 positive, 6 negative. And what I noticed very quickly is we just found something that Hollywood uses all the time, and that's carbon 12. Uniquely, they say the devil is inside of you. And the reason they say that is because somebody in chemistry class at one point in time realized that carbon tissue is in your body, and it always has 6 protons, 6 neutrons, and 6 electrons. So that devil idea is probably from chemistry class for some horror film director, and that's where that 666 number could have came from, who knows. But it ties in as a cute example. The only thing that else we need to talk about is ions. So just a brief introduction, we're going to see this in other videos as well. If we were to change this number, we'd have to be careful because then we'd have charge. So if we would change this number to an example where carbon has protons, neutrons, electrons again, it's got to be 6 protons or it's not carbon. Here, neutrons is kind of irrelevant, but the number of electrons, if this is a 6, we had no charge on carbon. And if we have no charge on carbon, what happens is it's just in its elemental form. But as we'll see later, carbon oftentimes likes to have 10 electrons. So when you think about charge, think about these two and subtract. If you go 6 minus 10, that's going to be carbon with a -4 charge. That would be called carbide. If you don't like negative numbers, one way to think about it is zeros here. We have 1, 2, 3, 4, 5, 6 protons. But if we have 10 electrons, we're going to take 6 to be neutral, but then we need 1, 2, 3, 4 more electrons, and that takes us in that -4 kind of direction. So a lot of students don't like positive negative numbers. Just remember that when you're looking for ions in that simplest form, it's protons minus electrons. A lot of students like to go backwards because when they hear the word lose, they want to go negative, but in chemistry that'll be positive. And sometimes they want to hear the word gain, but when you're gaining electrons that are negative, you become negative. And we'll get more practice in another lecture for that. So see you next time.